Let's talk about counting. Now, I'm sure you already know how to count, but the thing about calculating probabilities is that we need to know the size of the sample space. And some sample spaces are just way too big to count by hand, just by listing all of the individual outcomes in the sample space and then actually counting them. For example, think about the number of 5-card hands that you can draw from a 52-card deck, or the number of possible lottery drawings with lottery numbers from 1 to 60. There are just way too many possibilities to list. It would take you forever to count. But to calculate probabilities for these situations, we need to know how big the sample size is. So we're going to need to figure out some tricks for calculating the size of large sample spaces or large collections of outcomes. So here's our first trick. It's actually related to something that we've seen before. Suppose I need to choose an outfit for my drawer containing, my drawer contains 3 shirts and 2 pairs of pants. How many outfits are possible? So these 2 choices that I need to make are totally independent of each other. I could wear my t-shirt and jeans, or my polo shirt and jeans, or a plaid shirt and jeans, and so on. Same with wearing khakis for my pants instead of jeans. So because my choice of what pair of pants to wear is completely independent of my choice of what shirt to wear, we can totally fill out this table where there's 1 row for each pair of pants and 1 column for each shirt. And there are 2 pairs of pants that I might choose and 3 shirts that I might choose. And if you count up all the individual outfits that I could have, there are 6 of them. And that's not a coincidence, because 2 rows times 3 columns is 6. And actually that happens in general. If you have 2 choices to make and they're independent, and you have m choices for the first one and n choices for the second one, then the total number of possibilities you have is just the product, m times m times n. So for example, how many ways are there to choose a 4-letter password if we allow repeated letters? So for the first letter, there are 26 choices. For the second letter, there are also 26 choices because we're allowing ourselves to repeat letters. For the third letter, there are 26 choices. And for the fourth, there are again 26 choices. And these choices are completely independent of each other, and so it's just multiplied together these numbers of possibilities. And we get 26 to the 4th, which is a fair number of 4-letter passwords. Let's look at some other examples. How many ways can I rearrange 10 tiles numbered 1 through 10? So imagine laying out a bunch of tiles, say your 8 tile, and then your 6, and then your 1, and then your 10, and so on. How many ways are there to do this? Well, let's think about the choices that you have to make along the way to actually determine an arrangement of these tiles. So you have to pick a first choice, and then you have to pick a second one, and then you have to pick a third one, all the way down to your 10th tile. How many choices are there for the first one? Well, at the beginning you have 10 tiles to choose from, so for your first, there's 10. Okay, now for your second choice, how many tiles are there to choose from? Well, you've already chosen 1 tile, so there are 9 remaining to choose from. Now you might think, aren't the tiles that you have available for your second choice dependent on what you chose for your first choice? That's true, but the number of tiles available for your second choice, it doesn't depend on which tile you chose for your first choice. It just depends on the fact that you chose a tile for your first choice. So no matter what you chose for your first choice, there are 9 tiles available to choose from for your second choice, and 8 tiles for your third choice, and so on. 7, and then 6, and then 5, 4, 3, 2, 1. So this is a pretty big number. You probably wouldn't want to calculate this by hand, but we could dump this into a calculator and see what we get. Turns out this is 3,628,800. So lots of possible ways to arrange those tiles. For another example, let's figure out how many ways we can choose a president, a secretary, and a treasurer from an executive board of 8 people. So we want a president, a secretary, and a treasurer. So for the president, there are 8 people that we could choose. For the secretary, well, we've already chosen a president, and the president shouldn't be the secretary. I guess implicit in this situation is that the president, secretary, and treasurer should be different people. So when we come to choose a secretary, we've already chosen a president, so there are only 7 people left to choose from. And then when we choose a treasurer, there are only 6 people left to choose from. So our total number of possibilities is 8 times 7 times 6. This is 336 possible ways of choosing a president, secretary, and treasurer. All right, let's see if we can figure out how many ways can we place a king, a queen, a bishop, a knight, and a rook on an 8x8 chessboard. I'll use abbreviations for these. King will be a K, queen will be a Q, bishop will be a B, knight will be an N, that's what chess players use to abbreviate knight, and rook will be R. Okay, so we need to decide where are we going to put the king, the queen, the bishop, the knight, and the rook. So for the king on an 8x8 chessboard, there are 8x8 squares, so that's 8 times 8. That's 64 squares altogether. So for the king, we could put the king anywhere, so that's 64 possibilities. For the queen, well, we can put the queen anywhere except where the king is, so there are only 63 squares left to choose from. And then for the bishop, we can put the bishop anywhere except where the king and the queen are, so that's 62 possibilities. And for the knight, 61 possibilities. And for the rook, 60 possibilities. Okay. And since all of these numbers of possibilities are independent, we can just multiply them all together. So 64 times 63 times 62 times 61 times 60. So that's 914,941,440. So that's the number of possible ways of arranging these chess pieces on a board. And this is just one of each of these pieces. Of course, a full chessboard has multiple of each of these and all the pawns. Well, if you look at these 3 examples, they all have a few features in common. So what these have in common is that once we've made a choice, we can't choose the same thing again. So, for example, if you think about the president, secretary, treasurer example, when you chose someone to be a president, we couldn't choose them again to be the secretary or treasurer. And also the order in which we made our choices matters. So again, thinking to the president, treasurer, and secretary, we chose the president first, and the secretary second, and then the treasurer. If we chose the same people but in a different order, a different person would be the president. So the order that we chose things in made a difference. In these types of situations where you do not allow yourself to replace items, and the order that you make your choices matter, there's a nice formula for the number of possible ways to make your choices. In general, the situation is this. If you have n items to choose from, and you're going to choose r of them without replacing chosen items, and then you arrange those R items in some order. So if you look back at the examples on the previous slide, all of them were were of this type of situation. In this situation, the total number of ways of making your choices are n times n minus 1 times n minus 2, all the way down to n times r, n minus r minus 1, or sometimes you'll see this written n minus r plus 1. Okay. So there are that many ways to arrange the r items that you've chosen. So for example, if you're going to choose 5 items from 7 possibilities, that would be 7 times 6 times 5 times 4 times 3, and then you stop when you have 5 things listed in this product. So 7 times 6 times 5 times 4 times 3 would be the result here. So let's use this idea. How many ways can we choose a first, second, and third prize in a dog show? So just to check, once you choose a first prize, you can't give the second prize to the same dog, so we can't replace the dogs into our pool of possible winners. And also, the order that you make your choices matter in this case, because if you choose the same dogs but in a different order, a different dog will come out getting first prize. So we aren't replacing, and order matters, and so this means we can use the formula that we just worked out. So we have, we don't know how many dogs are in the dog show. Let me say there are 20 dogs in the dog show. So there are 20 possible choices, and we need to choose 3 total. So the total number is 20 times 19 times 18. And we have 3 factors in this product now, so we can stop with writing out all of our multiplications. So 20 times 19 times 18, that's 6,840. So there's 6,840 ways of awarding prizes to dogs in the dog show. For another example, let's look at how many ways we can arrange 100 deck chairs on the Titanic. So there are 100 things to choose from, but sort of implicit in the way that this is stated is that we're actually going to choose all 100 and just arrange them in some order. So we start at 100 and then times 99, times 98, times 97, and so on, all the way down to, eventually we get to times 2 and then times 1. So I won't actually calculate what this is because it's an enormously large number, but if you could calculate it, this is how many ways you could arrange the deck chairs. If you look at both of these examples, from situations like this, we tend to get large products of numbers, so big products with lots of different numbers multiplied together, and always the numbers that are multiplied together start at some value. So in this example, it was 100, and then they decrease by 1 each time you go down, and either they stop at some point, like at 18, or they go all the way down to 1. This is such a common thing that mathematicians actually abbreviate this situation. And here's the notation that they use to abbreviate this situation. When you have a product of all of the numbers from some starting point n down to 1, that's called n factorial, and it's just n with an exclamation mark. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1, and if you multiply these all together, you'll find you get 120. It seems like, using this definition for the factorial, it seems like 0 factorial wouldn't make sense, but mathematicians sort of have all agreed that 0 factorial should be 1. the reason for that is it makes lots of other formulas that have factorials in them make sense if you just sort of declare that 0 factorial is 1. So that huge product from 100 times 99 times 98 and so on down to 2 times 1, another way to write this would be 100 factorial. All right, now if you think about the ways of choosing all of the different, the number of ways of choosing our things and then putting them in order, that was actually a big product of numbers like this, and each number is one less than the one before it. This comes up often enough that it actually has its own name. It's called n permute r, like this. So for example, 5 permute 3 would be 5 times 4 times 3. If you work that out, that comes out to 60. This looks a lot sort of like a factorial, except the tail end of it is missing. There's no times 2 times 1 here. Well, you can still write this in terms of a factorial in the following way. So n permute r is n factorial divided by n minus r factorial. So just for example, 5 permute 3, we know it should be 60, but let's use the formula to see that the formula does produce 60. So this is 5 factorial over n minus r is 2, so 2 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. And 2 factorial is 2 times 1. And you can see that once you simplify this, you get 5 times 4 times 3, just like we got before, and that's 60. So n permute r actually has this nice formula involving factorials. So let's use this idea on an example. How many ways are there to choose a 4-letter word and a 5-digit number if we don't repeat any letters or digits? Okay, so to make these choices for our 4-letter word and our 5-digit number, this actually is sort of in 2 pieces. There's choosing a word from the letters and then choosing a 5-digit number. So let's look at those 2 separately. First the word and then the number. So to choose a word, we're choosing 4 letters from all the letters that are possible, which in English anyway is 26. And since it's a word, the order that you put them in matters. Okay, for the number, well, we're choosing 4 digits from 10 possible digits, 0 through 9. And again, because it's a number, order matters. So for both of these, we can express the number of possibilities using n permute r. So for the word, we have 26 possibilities, and we're choosing 4 to put in order. So it's 26 permute 4. For the number, we're choosing 5. This should be 5 right here, not 4. We're choosing 5 digits from among 10 digits. So that would be 5. I've got these backwards. This would be 10 permute 5. Now, since how we choose the word and how we choose the number are independent from each other, we can just multiply these numbers of possibilities. So for our total, we get 26 factorial over 26 minus 4 factorial times, and then for the number, we get 10 factorial divided by 10 minus 5 factorial. So this is 26 factorial over 22 factorial times 10 factorial over 5 factorial. Now, one problem with calculating permutations using NPR is that, or n permute r, is that the numbers involved, if you try to multiply out the factorials, the numbers involved get very large very, very quickly. But also, in this sort of fraction with the factorial in the numerator and the denominator, a lot of canceling will happen. And so if you know ahead of time to do the canceling before you calculate all of the multiplications, you'll save yourself a lot of work. Now, calculators usually have a factorial button, but unless they know ahead of time that you're going to divide by another factorial, your calculator won't know that it will be able to do all that simplifying, and it might produce a number that's so big that it actually can't contain the number. It just has too many digits for the calculator to keep track of all of the digits. But many scientific calculators have a button for n permute r. So if you look at your scientific calculator for something that looks like n permute r, n capital P and then r, often you'll find it as a shift function on some other key on your calculator. On my calculator, it's shift 2, it looks like. So I can do 26 and then do my permute button, 22, and that gives me a huge number, and then times 10 permute 5. And I get something like 1.34 times 10 to the 131. So this is about almost a 1 with 131 zeros after it. So a ridiculously huge number. I see now that I've missed a factorial right here. So getting really, really large numbers out of these permutation type situations is not at all unusual. Except for very small examples where your numbers are pretty low, you'll want to let a calculator do the heavy lifting on the calculations, because otherwise it'll take you forever.